Hello guys, this is CodeNCode and this is one of the lectures in the graph theory part 1 series. In this lecture we are going to see how we can find articulation point in the given graph. Prerequisite for this lecture of course is the lecture where we have already studied how we can find bridges, because in the bridges lecture I have already explained some of the concept that I am going to refer directly, like the concept of DFS tree. So in the comment section of the bridges video I've seen it was not clear to some of the student that how the in time and low time is calculated. So I am going to run through an example in this lecture so that the things gets even clear, or for the guys who for which it was not clear, it becomes clear. So what here we have, since there are like 13 nodes, that is why we are having two arrays of size 13. This array would store the in time of the node. In time is the time at which you enter a node, and low time is indicates that the time or the ancestor, the lowest ancestor you are directly connected, the lowest ancestor to which you can reach using some of the back edges. Now we initialize the timer with 1. So let's start. From the main function we would make a DFS call to node 1. So in timer and low time initially would be equal to the timer, which is 1. So we would initialize the in time and low time of node 1 to be 1, and this would indicate the in time of node 1. For each node I will also write down the in time of each node right next to it, so that we initialize the in time and low time of node 1. Now we would increment the timer. It would of course be 2. Now from node 1, suppose we made a DFS call to node 2. So the in time and low time of node 2 would be equal to timer, and we would increment the timer. From node 2, suppose you went to node 3. So in time and low time of node 3 is 3, and we incremented the timer. Suppose from node 3 we went to node 4. So in time and low time of node 4 would be 4, since the timer was 4, and then we incremented the timer. Now as you see, node 4, in the adjacency list of node 4 we have 3 and 2. Now for node 3 we would ignore it because this is parent of node 4. Node 3 is parent of node 4 in the DFS tree. That is why we would ignore this edge. But the second edge is actually a back edge, because this edge connects node 4 to a vertex which is already visited and is not parent of it. So it must be an ancestor which is not parent, so we would minimize the low time. So this must be a back edge. Since this is a back edge, so we would minimize the low time of node 4, because using this back edge node 4 can reach an ancestor 2. So we would minimize the low time of node 4 to be low time of node 4 is equals to minimum of low time of node 4 comma in time of node 2, because node 4 is connected to node 2, and we would minimize it by taking the in time of node 2. In time of node 2 is 2, so low time of node 4 would become 2. So now you see node 4 using some back edges can reach node 2 whose in time was 2. We would always keep here the low time, the in time. So now node 4 can reach a node which was discovered at time 2. So the in time indicates the time at which this node was discovered. So we see node 2 was discovered at time 2, and since node 4 can reach node 2 using some of the back edge, that is why the low time of node 4 is equals to 2. Now the work of node 4 is completed, so we would track back to node 3. After that, node 3 would check whether this subtree would survive if you disconnect or if you remove node 3. So you see, since we are if you consider the DFS tree of it, so node 4 is actually a subtree of node 3, right, in the DFS tree. Now if you remove this vertex, the problem is that subtree is the only subtree which is getting the thread to be disconnected. If you remove this node, so what how we confirm whether this subtree would survive or not, we would confirm it using the load time. So we would check the load time of node 4. Load time of node 4, since we have returned from node 4 to node 3, that is why we would check the load time of node 4, whether this subtree can survive or not. So load time of node 4 must be smaller than the load time, load time of node 4 must be smaller than the in time of node 3. If for any node whose in time is smaller than node 3, every single node who is having, of course, the load time smaller than the in time of every node which is having load time smaller than the load time of node 3 is actually ancestor even for node 3, right? So only these two nodes are having in time smaller than the in time of node 3, and both of these are actually ancestor of node 3. So even if you remove this node and load time of node 4 is equals to either 1 or 2, which is smaller than the in time of 3, that means that node 4 is connected to one of the ancestor of node 3. So even if you remove that edge, it is still connected to the ancestor, which means it is still connected, and this subtree is still not disconnected, which means even if you remove this vertex, this subtree is still connected, which means this is not an articulation point with respect to this subtree. So for that, to confirm a node to be an articulation point, we check for its in time and the load time of the node from which we have recently made a backtrack. So node 4 is having load time to be 2, while the in time of node 4 is while the in time of node 3 is 3. So we see the load time of node 4 is 2, which means it is connected to ancestor, and hence even if you remove this node, this subtree is still connected. So this vertex cannot be an articulation point, because even if you remove it, the other subtree is still connected. So this cannot be an articulation point. After checking whether it is articulation point or not, it would minimize its load time as well using the load time of this node. Why? Because this node is the child of node 3. That is why if this node can reach some other ancestor, then this node 3 can also reach that ancestor. Reason, since node 4 can reach some of the ancestor which was discovered before node 3, it must have a path from node 4 to that ancestor, right? Using that path, node 4 is reaching the ancestor which was discovered before 3. So what node 3 can do, since it has an edge from 3 to 4, it can reach from node 3 to node 4, and then from node 4 it can use the same path to reach that ancestor. That is why if load time of node 4 is 2, so load time of node 3 would be at least 2. So we would minimize the load time of node 3 as well. So load time of 3 would be load time of 3 comma load time of 4. Load time of 4 was 2, so load time of 3 also gets updated, and it is also 2. Now load time can never be updated using an edge which connects a node to its parent. So for 3, I cannot update its load time using this edge, because this connects node 3 to its parent. So the edge which directly connects a node to its parent, that edge can never be used to decrement or update the load time of a current node. So that is why initially the load time of node 3 was only 3. It was not equal to the in time of node 2, because this edge cannot minimize the load time of node 3. But these edges can minimize, because we are now not using the edge which connects node 3 to its parent, but we are using a different path. Now work of node 3 is completed, so it would track back to node 2. Now node 2 will check whether my subtree, which is this subtree, whether the subtree rooted at node 3 would survive or not. So for that, you would see the load time of node 3. The load time of node 3 is 2, which means this subtree is not connected to some of the ancestor of node 2. which this subtree is not connected to some of the ancestor which were discovered before node 2. What that means, if you remove this node, this subtree will get disconnected because there is no path from this subtree to one of the ancestor which was discovered before node 2. So load time of node 3 is not smaller than the in time of node 2. That is why this particular vertex is actually an articulation point, and hence node 2 is articulation point. After that we would go to node 1. Node 1 will also check the same thing. Now here I haven't done one thing, that after checking for whether node 2 is an articulation point or not, it would also minimize its load time using this. But load time of node 3 is already equal to the load time of node 2, so there would nothing would happen there. So after the work of in the adjacency list, since initially from node 2 we had made a DFS call to node 3, and so only this part was discovered. Now in the adjacency list of node 2 there is also an edge, which is this, which connects node 2 to some of the vertex which is already discovered. So this is a back edge. Of course this is a back edge because this edge is connecting node 2 to one of the vertex which is already discovered, and this edge is not connecting node 2 to its parent, since parent of node 2 is 1. So this is a back edge. Yes, this is a back edge, but will it minimize the load time of node 2? Not, of course, because this is not an ancestor. So even though if you write since we have found a back edge, so we would try to minimize the load time of node 2. So load time of node 2 is equals to minimum of load time of node 2 comma load in time of node 4. So you see no time or load time of node 2 would not be changed. After doing this, we would track back, because in the adjacency list of node 2 is completely traversed. So we would track back to node 1. After reaching node 1 would check whether this subtree would survive if I am removed. So we see that this subtree would not survive if node 1 is removed, because if you remove node 1, this subtree would get disconnected from the rest of the graph. So to confirm that, we would check, of course, the load time of node 2. Load time of node 2 must be smaller than the in time of node 1. But wait, there's a problem. There is no node which can have load time smaller than the root. Sorry, there is no node which can have load time smaller than the in time of root, right? Because there is no node which was discovered before node 1. So this is a problem, because no matter what graph you choose, root will always be like I am the articulation point, no matter whether it is an articulation point or not. Now see, the load time of node 2 is actually 2, while the in time of node 1 is 1. So we see that load time of node 2 is not smaller than the in time of node 1. So node 1 is an articulation point. In this case, yes, this is an articulation point, but there are cases where root is actually not an articulation point. But to check whether a current node is an articulation point or not, what we are doing, we are checking for that node from which we have made a backtrack to node 1. So for that node we are checking, okay, what is your load time? I am an articulation point if your load time is not smaller than the in time of me. That is, you must be connected to some of the ancestor which was discovered before me, but there is no ancestor which was discovered before root. So root would always come out to be an articulation point, no matter whether the root is an articulation point or not. So that is a problem. So we have to counter that fact. Let me show you an example where the root is not actually an articulation point. Here you see, if you see, node 1 would make a DFS call to node 2, node 2 made a DFS call to node 3. So now since this edge is a back edge for node 3, if you are following this path, of course, from node 1 to node 2, node 2 to node 3, this edge is actually a back edge for node 3, so it would minimize its slow time. Its slow time would become 1, right? After that it would return to node 2. Now when you made a return or when you come back to a node, this node would check whether this subtree would survive or not. For that, you would check the load time of node 3. Since load time of node 3 is smaller than the in time of node 2, in time of node 2 was 2, because at time 2 node 2 was discovered. So since the load time of node 3 is smaller than the in time of node 2, that means even if you remove it, it is still connected to some of the ancestor which was discovered before 2, which means this would still be connected. Of course, if you remove node 2, node 3 is still connected, it is not disconnected. That is why this cannot be an articulation point. After that, you would go back to node 1. Node 1 would check whether this subtree would survive or not. For that, it would check the load time. Yeah, of course, you would also minimize the load time of node 2, and load time of node 2 would become 1. Now node 1 would check whether this subtree would survive or not. For that, it would check the load time of node 2. Load time of node 2 is 1 because node 2 can reach node 1 via this path. But the load time of node 2 is not smaller than the in time of node 1. That is why node 1, we would report node 1 to be an articulation point, but we see clearly node 1 is not an articulation point. So keeping that thing in mind, we check whether the current node is an articulation point or not only if the current node is not actually the root. If the current node is root, that we would not check whether this is an articulation point or not, or we would not compare their load time and in time if the current node is root. So if I show you the implementation, this is, first of all, this is cpalgorithm.com, and this is the website which I personally prefer to learn algorithms. So this website is actually an English conversion of the website emacs.ru/algo, because Emacs is written in Russian language. Of course, either you'd use Google Translator, or you can read the articles which were written there in Russian language. You can use this site to learn the same algorithms in English. So this website contains a lot of the algorithms you would want to learn, like fundamental of algebra or number theory, sieve, everything, or data structure, tree, disjoint set, and so on. So this is the website I personally prefer. So here's the article which you can learn for finding articulation points. So what I was going to do, I was going to show you the implementation. Now this is the DFS which finds the articulation point. Now see, there are two parameters. First is the node, second is the parent of the current node. Since it is important for a node to have the information about its parent, so that when you are traversing the adjacency list of this node, you can actually ignore the edge which directly connects the node to its parent, because that edge we never use to minimize the load time, as explained earlier. That is why for each node it is important to have the information about its parent. That is why we are having a parent parameter as well. So from the, suppose this was our main function, we initialize the timer to be 0, we assign the visited is a vector of size n, of course. So we initialize all of the values to be false. We fill the in time and load time with -1. It is not necessary to fill the load time and in time with -1, because load time and in time will always get overridden when you reach a DFS node. So these two steps are not necessary, actually. You can leave this. So since the graph can be disconnected, there may be more than one connected component of the graph. So that is why for each node which is not visited, we would make a DFS call to that to find the articulation point in that connected component. But you see, there are two parameters while we are passing only one. So this node would become, sorry, yeah, so this node would become the current node which is passed from the main function will be considered as the root of that particular connected component. Since that node is root, so its parent is equals to -1. Since for a tree, for a root in a tree, there is no parent of the root. That is why, since this node would become from the main function to which we have called the DFS function, that node would become the root, and since the root have no parent, that is why p is initialized with -1. So -1 would indicate the current node. P is equals to -1 would indicate that the current node is actually a root. And as explained in the slide, if the current node is -1, if the current node is root, which means if p is equals to -1, we would not check for whether the current node is articulation point or not. So if you start from the beginning, you see, as you reach a node, you would mark it as visited. You initialize it in time and load time to be timer plus plus, which means first we would use the value, then we would increment it. And we are initializing the children to be 0. Children is used to count the total number of subtrees. Like here, you see, suppose node 1 was the root of this connected component. So you see, node 1 would make a DFS called suppose here, so you would reach 2 and then 3, and then you would track back to 2 and 1, and 1 would make another DFS call to 2. Sorry, this is, oh, I'm messed up with the numbering. So consider this node to be 1, this is 2 to 3, and this is 4, 5, 6, right? So from 1 you reach to 2 and then 3, you track back to 2, track back to 1. Now the root would make one more DFS call to 4, and then you would reach 5 and then 6. So you see, in the DFS tree, node 1 is having 2 subtrees, right? This as one subtree, this as another subtree. So if the root is having more than one subtrees in the DFS tree, then the root itself is actually the articulation point. So this is criteria for root, and for the rest of the nodes we have the same criteria in which we check the load time and the in time. So for root, we would count the total number of subtrees in its DFS tree. We see there are 2 subtrees in the DFS tree of this connected component, hence the root must be an articulation point. If you see in this example, node 1 would have only one subtree in the DFS tree. From node 1 you would make a DFS call to this and this, so node 1 would have only one subtree in this case. That is why the root would not be the articulation point in this point, in that graph, but in this graph root would be the articulation point, because in the DFS tree it is having two different subtrees. So that is why for that we are having a children count, which basically counts the total number of subtrees rooted at this point, at this node. So we initialize the children count to be 0. In the adjacency list of current node, I would call this as this node, this 2 node as child, and this as current node. So if the child is equals to parent, of course this current edge which is connecting you to child is actually connecting it to its parent. So that is why if the current node is parent, if the current child is parent, that we would not do anything, or we would simply continue for the next iteration. Otherwise, if this node is visited, which means you have found a back edge. So you are at node 3 and you are traversing your edge list. You found first edge was this, but this is your parent, so you would do nothing. And then the next edge you found was this, which connects node 3 to node 1, which was already visited, which means this edge is actually a back edge. So when you find a back edge, what you do, you simply minimize the load time of the current node. So if the child is actually already visited, which means it is an ancestor, actually this can be an ancestor. That is why we would minimize the load time of the current node to be in time of that child node. I'm calling this child, but this can also be ancestor, because I cannot refer this as the other node every time. I can call this the current node, I cannot call it the other node every time. So that is why I usually call it child. So if the child is actually visited, which means it can be ancestor, that is why we would minimize the load time. This edge actually indicates the presence of the back edge. When you find a back edge, you would minimize your load time. That is what we are doing here. If not, if the current node is not visited and current node is not actually your parent, which means this is actually a forward edge. When you find a forward edge, what you do? You do a DFS call to that node. So you would make a DFS call to that node and the current node would become its parent. So you made a DFS call to that. After you return from that DFS, what you do, you minimize your load time to be load time of that node or the child node, and you would see whether the current subtree can survive or not. So the current subtree is rooted at TO, that is 2. So you will see whether the load time is greater than or equal to in time of current node. If the load time of that child is greater than or equal to the in time of the current node, and the current node is not actually root, because we have to test it if the current node is not root. So if the current node is not root, then we would check whether the load time of the child is greater than or equal to in time of V, which is current node, which means this subtree is not connected to some of the ancestor which was discovered before V. That is why if you remove V, this whole subtree would get disconnected, and hence this must be an articulation point. That is why we are calling the function is cut point. Is cut point is a function that you would define, of course, whatever you want to do with this cut point or articulation point. Or if you are counting the total number of articulation point, of course you can increment the count. But since the same node can be found as articulation point by many subtrees, that is why it is a good idea, if you are counting the total number of articulation point, it is a good idea to use a set and simply insert this node into that set, and at the end you can print the size of that set. After that, since this we made a DFS call to this node, which means we are finding a new subtree. When you are finding a new subtree, of course you would increment the child count, and if the current node is root and the child is more than 1, that is why the current node itself, the root itself, is the articulation point, and hence current node which is root actually is also marked as articulation point. So this is how you find actually the articulation point. Of course, you can read about articulation point on this website, cpalgorithm.com, which is really good website because it comes with implementation as well as the practice problem you can find here. So it teaches algorithm, and that gives the implementation usually in C++, and then also provides you practice problems which you can use to practice the current algorithm that you have just studied. It also comes with it also provides the proof of most of the algorithms, so that is why I personally prefer this. There's one more article you can read about the DFS tree and finding bridges and articulation point. That article is this. I will be posting the link of this article and this article both in the description of this video. I will highly recommend you to read this article because this not only explains you DFS tree in detail, but also it explains some of the concept you can use of DFS tree to solve the problem, which are really good. Like let me show you some example. In the example problem, it is explaining this E problem, Burton roads. I think I have made video editorial for this, but you can see it explains Burton roads, which is just let that open. So it is explaining how you can use the same algorithm, the concept of DFS tree, you can use that to solve this problem. This problem you see is actually rated 2100. Now after explaining that, this article move on to explain more of the concept, which one of the concept is cacti or cactus. There is concept in the graph theory of cactus. So there is a problem also which is again a div to E problem, which would be roughly 2000 or 2100 rated. I don't have actually idea. So this is also explaining that problem as example problem. So you can learn a lot from this article. So I'll be posting the link of this article and the link of this article in the description. So do check, just make sure you read this article as well as this to gain your knowledge base. So this was all for this lecture. Thank you guys for watching. If you have any query, of course you can post it down in the comments. So this was all. Thank you, and till the next video drops, keep coding. Thank you.